Welcome back to the deep dive. Today, we're getting into the nitty-gritty of making sure our data structures don't turn against us.
Yeah, exactly.
We're taking a deep dive into the fascinating world of AVL trees, and we're using Hello Algo Chapter 7.5 as our guide here.
That's right. We're focusing on a classic problem, really, that can pop up with standard binary search trees, BSTs, and how AVL trees provide this really quite clever solution. If you've ever worked with data and wondered why search performance can sometimes be, well, inconsistent.
Or how some systems just stay so snappy, even with tons of updates.
Exactly. Then this is for you. Pay attention.
So, our mission in this deep dive is to really pull apart the mechanics of AVL trees. We want you to finish this conversation understanding precisely why they are such a valuable tool.
Yeah, for managing dynamic data efficiently.
Think of this as the understanding that lasts, a lifetime, not just something for a quick test.
Okay, so let's start by laying out the issue itself. Binary search trees, they're designed for speed, right?
Right. Logarithmic time, ideally.
Ideally. Operations like searching, inserting, deleting nodes, they should take O log n time, where n is the number of nodes.
And that logarithmic scaling is fantastic for large data sets. It means adding millions of items barely bumps up the search time.
But, and this is the kicker, that O log n performance relies entirely on the tree staying, well, tree-like, balanced, essentially.
Okay, so what happens if you start messing with it a lot, removing nodes frequently?
That's exactly where things can go wrong. The source material points out that after a series of insertions and removals, a standard BST can actually lose that nice structure.
Lose it how?
It starts to look less like a bushy balanced tree and more like a single long chain of nodes.
Like a straight line, almost like a linked list.
Precisely.
Yeah.
And the source shows this really clearly. Figure 724, it demonstrates how just a couple of removals can kind of collapse parts of the tree.
Okay.
And figure 725 shows how inserting nodes in a certain specific order can make the tree lean heavily to one side. Dramatically lean.
Right. And when your tree basically becomes a linked list, you completely lose that logarithmic speed advantage.
You do. Searching goes for maybe a handful of steps, hopping down branches.
To potentially scanning nearly every single node in that line.
Which totally changes your time complexity. That beautiful O log n performance, it degrades all the way down to ON, linear time.
Which is a huge difference.
Oh, massive. On 1 million nodes, think about it, 20 steps versus maybe 1 million steps. It's a performance catastrophe for large applications.
So how do we stop that from happening? This is where the AVL tree comes in, right? The one from Adelson, Velsky, and Landis back in the 60s?
Exactly. The AVL tree is, at its core, a binary search tree. It has all those properties.
Yeah.
But it comes with an extra ironclad guarantee. It must also be a balanced binary tree at all times.
So it's enforcing balance rigorously.
Absolutely. Alongside the BST rules, the whole point is to prevent that degradation we talked about and ensure that all your main operations, adding, removing, searching, consistently hit that efficient O log n performance.
Okay, so how does it do that? How does it achieve and, maybe more importantly, maintain that balance? That sounds like the tricky part.
It is the core of it, yeah. And to really get it, the source highlights 2 key concepts we need. First up is node height.
Node height. That's the distance from a node down to its farthest leaf, right? Counting the edges.
That's the one. And the definitions here are really important. A leaf node, one with no children, has a height of 0.
Okay.
And maybe slightly counterintuitively, but it works out mathematically. A null node, like an empty child pointer, is defined as having a height of -1.
-1, got it.
And AVL tree nodes actually need to store this height value. There's usually a helper function, the source calls it update height, that calculates and sets a node's height.
How does it calculate it?
It looks at the heights of its left and right children's subtrees, takes the maximum of those 2 heights, and adds 1.
Max height of children plus 1.
Yeah.
Okay, so height tells us how deep a branch goes. What's the second concept?
The node balance factor.
Balance factor, okay.
This one's a pretty simple calculation. It's just the height of the node's left subtree minus the height of its right subtree.
Left height minus right height. Makes sense. What about a null node?
A null node has a balance factor of 0. The source shows a balance factor function that does this calculation.
And this balance factor. This is where the AVL rule comes in, isn't it? This is the strict check.
Exactly. This is fundamental. The core property of any AVL tree is that the balance factor of every single node in that tree must be between -1 and 1 inclusive.
So -1, 0, or 1. That's it.
That's it. If any node has a balance factor less than -1 or greater than 1, it's considered unbalanced.
And that's the trigger. That's when the magic happens.
That's the trigger. When a node becomes unbalanced, the AVL tree doesn't just, accept it, it fixes itself. And it does this using rotation.
Rotations. Okay, tell me about these.
Rotations are the core mechanism. There's specific ways to restructure a small part of the tree by cleverly rearranging the node pointers. And the really brilliant part is that they restore the balance. They fix that balance factor issue without breaking the binary search tree property. The order of the nodes, if you read them in order, stays exactly the same.
Wow. Okay, so balance is restored, but searchability isn't broken. How many types are there?
The source describes 4 main types, and figure 732 actually summarizes them nicely. Let's start with the simpler ones. First, the right rotation.
Right rotation. When is that used?
This is for when a subtree becomes too heavy on the left side. So the unbalanced node has a balance factor greater than 1.
Left-leaning.
Left-leaning, exactly. Figure 726 shows the basic idea. Imagine the unbalanced node, let's call it P, and its left child, Q.
Okay, P is unbalanced, Q is its left child.
You basically swing P down and into the right. Q comes up to take P's place as the root of that little subtree.
So Q becomes the new parent.
Yes, and P becomes the right child of Q.
P swings down right, Q comes up. Got it.
Yeah.
But I see figure 727 looks a bit more complex. What if Q, the node that came up, already had a right child? Let's call it R. Where does R go?
Good catch. That's the key pointer adjustment in that case. R, which was Q's original right child, can't stay there because P is moving into that spot, so R becomes P's new left child.
Okay, so Q's old right child becomes P's new left child. The pointers get shuffled around carefully.
Very carefully. And critically, after you do the rotation, you have to call that update height function on the nodes involved, usually P and then Q, to make sure their height values are correct again. Heights change after rotation.
Makes sense. Update the structure, then update the heights, and then there's the left rotation, which I'm guessing is the mirror image.
Exactly right. Symmetrical. This is used when a subtree is too heavy on the right side.
So the balance factor is less than -1, right-leaning.
Yep. Figure 728 shows it. Unbalanced node P, its right child Q. P swings down and to the left this time. Q comes up to be the new root of the subtree.
And P becomes Q's left child.
Correct. And again, figure 729 shows the slightly more complex case. If Q originally had a left child, R.
Let me guess. R becomes P's new right child.
You got it. Perfectly symmetrical pointer changes. And of course, you call update height on P and Q afterwards.
Okay, so these single rotations, left and right, handle cases where the imbalance is kind of straight down one side.
Yeah, you could think of it that way, like a straight line imbalance.
Yeah.
But sometimes the imbalance is more of a zigzag shape.
A zigzag.
Yeah, and in those cases, a single rotation, either left or right, actually isn't enough to fix the balance properly for the whole subtree.
Ah, okay. So that's where the other two rotation types come in, the double rotations.
Exactly. First is the left-right rotation.
Left-right. What kind of imbalance triggers this?
This happens when the main unbalanced node is left-heavy, so its balance factor is greater than 1.
Okay, left-leaning.
But the imbalance isn't caused by its left child being left-heavy too. Instead, the problem child is the right child of the left child. It's like a zigzag inwards.
So P is left-heavy. Its left child Q is actually right-heavy. That's the zigzag.
Precisely. Figure 730 illustrates this. You fix it with a two-step process. First, you perform a left rotation on the child node, Q.
A left rotation on Q. Why?
That rotation effectively straightens out the zigzag. It turns the QR part into a straight left-leaning line.
Ah, okay. So you fix the inner kink first. Then what?
Then, after that first rotation, the whole structure looks like a simple left-leaning imbalance at node P. So you just perform a standard right rotation on P.
I see. Left rotation on the child, then right rotation on the parent. 2 steps. Left, right. Okay. And the right-left rotation must be the mirror image again.
You've got the pattern. Figure 731 shows it. The unbalanced node P is right-heavy, the F Nation.
Right-leaning.
But the actual imbalance deep down comes from the left child of its right child. So P's right child Q is left-heavy, the opposite zigzag.
Okay. So the fix is a right rotation on the child Q first.
Correct. Straighten out the zigzag.
And then a left rotation on the original unbalanced node P.
Exactly. Right rotation on child, left rotation on parent, right-left.
That's quite clever how the double rotations break down into combinations of the single ones.
But how does the algorithm or the code actually know which of these 4 scenarios it's dealing with, which rotation or sequence to use.
Yeah, that's crucial. The sources table 7.3 is really the key here. It lays out the logic clearly. It all depends on two things: the sign of the unbalanced node's balance factor and the sign of the balance factor of its child on the heavier side.
Okay, walk me through that logic, maybe using the table's examples.
Sure. Let's say you find an unbalanced node P, and it's left-leaning. Its balance factor is greater than 1.
Okay, BF1.
Now you look at its left child, Q, because it's left-leaning. You check Q's balance factor.
Right.
If Q's balance factor is 0 or positive, meaning Q subtree is also leaning left, or it's perfectly balanced itself.
That's the straight imbalance case.
Yes. In that case, you just need a simple right rotation on P.
Makes sense.
Go.
But what if Q's balance factor is negative? If Q's balance factor is negative, that means Q is leaning right, even though P is leaning left overall. That's your zigzag.
The left-right case.
Exactly. So you need the left-right rotation sequence, left on Q, then right on P.
Got it. And the logic for a right-leaning node P, BF1, must be symmetrical.
Perfectly symmetrical. You check its right child, Q. If Q's balance factor is 0 or negative, leaning right or balanced.
Simple left rotation on P.
Correct. But if Q's balance factor is positive, meaning Q is leaning left.
That's the other zigzag. Needs the right-left rotation.
Yeah.
Right on Q, then left on P.
You've nailed it. And typically there's a function, the source calls it rotate, that encapsulates all this decision logic. You pass it the unbalanced node, it figures out the situation based on the balance factors, and performs the correct rotation.
Okay, so that rotate function is like the AVL tree's chiropractor.
Yeah.
It adjusts things back into alignment.
Yeah, that's a good way to put it. Now let's connect this back to the actual operations, like adding or removing nodes. How do these rotations get triggered?
Right. Let's start with node insertion. How does that work in an AVL tree?
Well, the first part is exactly the same as in a regular binary search tree. You traverse down the tree, comparing values, to find the correct spot where the new node should be inserted according to the BST property.
Standard BST insertion. Find the null pointer where it fits.
Exactly. You insert the new node there, but then comes the AVL difference. You don't just stop.
This is where the balancing kicks in.
Right. You have to trace your steps back up the tree, starting from the parent of the node you just inserted, all the way back towards the root.
Following the path back up.
Yes. And at every node you visit on this path back up, you first need to recalculate its height, because inserting a node below it might have changed its height.
Okay, update height.
Then you check its balance factor. If you find a node whose balance factor is now outside that magic range of -1 to 1.
It's unbalanced.
It's unbalanced.
Right.
So you immediately call that rotate function we discussed, passing it this unbalanced node. The rotate function does its thing, fixes the balance at that spot.
And then you continue tracing up.
You continue tracing up, checking heights and balance factors, potentially performing more rotations if you find other unbalanced nodes higher up the path. You fix the balance from the bottom up. The source shows this logic integrated into an insert helper function.
Okay, tracing back up, potentially doing rotations at multiple levels. Does that add a lot of extra work compared to just sticking the node in like a normal BST?
It definitely adds some computational cost. Rotations involve pointer changes, height updates, balance factor checks. It's not free. But, and this is crucial, remember that the height of an AVL tree is guaranteed to be logarithmic, O log n.
Because it's always kept balanced.
Exactly. So that path you trace back up from the new node to the root, its length is at most O log n.
Okay.
And each rotation takes a constant amount of time, just shuffling a few pointers. So even if you have to do a rotation at every level on the way up, which is rare, the total rebalancing work after an insertion is still proportional to the height of the tree.
Which is O log n.
Right. So the overall complexity of insertion remains O log n. You're paying a slightly higher constant factor during the update, you could say, to guarantee that logarithmic performance overall, especially for searches later.
That makes a lot of sense.
Mm-hmm.
You invest a bit during insertion and removal to keep everything fast and consistent long term.
Yep.
What about node removal? Is it similar?
Very similar logic applies. Removal also starts, just like in a standard BST. You find the node you want to delete.
Okay.
Then you handle the different cases. If the node has no children, you just remove it. If it has one child, you replace it with its child.
And the two-child case, that's usually the tricky one.
Right. For the two-child case, the common approach, as the source describes, is to find the node's in-order successor that's the smallest value in its right subtree.
Okay, find the successor.
You copy the successor's value into the node you want to delete, and then you recursively delete the original successor node, which is now easier to delete because it has at most one right child.
Got it. So that's the standard BST removal part. Now the AVL part.
Just like insertion. After the node is physically removed, or after the successor's value is copied and the successor node is removed, you have to trace back up the tree.
Starting from where?
Starting from the parent of the node that was actually removed or replaced. You trace back up towards the root.
Not on the way up.
On the way up, at every node, you update its height, check its balance factor. If it's unbalanced, -2 or +2, you call the rotate function to perform the necessary rotations to restore balance.
Fixing it at bottom up again.
Exactly. This logic is typically handled in a remove helper function, similar to the insert helper.
So the rebalancing strategy after both insertion and removal is fundamentally the same. Trace back up the affected path, update heights, check balance factors, and rotate if needed.
Precisely. The trigger points are slightly different, but the reaction mechanism, the rebalancing path, is the same.
And what about node search? Does all this rotation stuff affect searching?
Thankfully, no. It's completely unaffected because the rotations, as we said, preserve the binary search tree property, the ordering of nodes. Searching in an AVL tree is absolutely identical to searching in a standard BST.
You just follow the value comparisons down the tree, left if smaller, right if larger.
That's all there is to it. The balancing machinery is purely for maintaining structure during updates. It doesn't interfere with lookups.
So given all this, where do AVL trees really make the most sense? Where do they shine in practice?
The source points to applications where fast, reliable search performance is really the top priority, especially when updates, insertions, and removals happen, but maybe not quite as frequently as searches.
Okay.
They're excellent for organizing and storing large data sets where you need that guaranteed O-log-N search time. You get predictable, rapid access no matter how the data was inserted.
Like database index systems. That's another example mentioned in the source, right?
Yeah. Exactly. Database indexes are searched constantly. You need those lookups to be super fast and consistent. Updates to the index structure itself still happen, of course, but often less frequently than the queries hitting it. AVL trees provide that performance guarantee.
Now, the source also brought up a comparison to another type of balanced tree, red-black trees.
Ah, yes, the other big name in balanced BSTs.
They both keep the tree balanced, but they do it differently.
That's the key distinction, yeah. The source highlights that red-black trees have more relaxed balancing rules compared to AVL trees.
More relaxed. How so?
They don't enforce that strict -1-to-1 balance factor rule on every single node like AVL trees do. They use node colors, red and black, and a set of rules about how those colors can be arranged to ensure the tree's height stays logarithmic, but it allows for slightly more imbalance locally than an AVL tree would tolerate.
Interesting. How does that difference in strictness affect performance?
Well, because the rules are more relaxed, insertions and removals in a red-black tree generally require fewer rotations or sometimes simpler restructuring operations compared to an AVL tree. An AVL tree might need more rotations to maintain its stricter balance after an update.
Fewer rotations. Does that make updates faster in red-black trees?
On average, yes. The source specifically notes that red-black trees tend to have a higher average efficiency for addition and removal operations. The rebalancing cost per update is often lower.
Okay, let me see if I can summarize that trade-off. AVL trees are more strictly balanced, almost perfectly balanced.
As balanced as a binary tree can be while maintaining the BST property, pretty much.
Which gives you perhaps the absolute best possible search time for a tree of that height because it's less deep.
Potentially, yes. The height is guaranteed to be very close to the theoretical minimum.
But you pay for that strictness with potentially more complex or more frequent rebalancing work during insertions and removals.
That's the trade-off.
Whereas red-black trees are a bit looser, a bit less strictly balanced. They still guarantee O-log-N height, but might be slightly taller than a comparable AVL tree in the worst case.
They allow a bit more variance.
Which might mean searches could be marginally slower than the absolute best-case AVL search. But they make up for it by potentially having faster average performance for insertions and removals because they don't need to rotate as often or as much.
That's a really good summary of the core difference. It's a classic computer science trade-off. Stricter guarantees versus potentially lower update overhead.
Right. So let's wrap up this deep dive. AVL trees are, well, they're a really brilliant refinement of the basic binary search tree.
They really are.
They introduce these core concepts of node height and balance factor. And they use these clever pointer rearranging operations, the rotation,
Left, right, right, left.
to dynamically maintain a very strict balance in the tree structure.
And the payoff is huge. This prevents the tree from degrading into those slow, list-like structures we talked about at the beginning.
Ensuring that all your key operations, searching, inserting, removing consistently, stay highly efficient, running in O log n time, even after lots and lots of changes.
That act of maintaining balance, whether it's AVL's strict approach or Red-Black's slightly more relaxed one, is absolutely fundamental for building data structures that perform predictably and efficiently, especially when dealing with data that changes over time.
And that leaves us, and you listening, with a really interesting point to consider. Given this trade-off we just discussed, AVL trees prioritizing that super strict balance for guaranteed fast searches, potentially at the cost of more work during updates.
Versus Red-Black trees, which are a bit more relaxed, possibly leading to faster average updates, but maybe not quite as tightly bounded search times.
How would you decide which structure is actually best for a specific application you might be building? Think about the mix of operations. Is your application going to be 99% searches and only where updates?
Or is it going to involve lots of rapid insertions and deletions, with searches being less critical, perhaps?
That specific context, the expected pattern of use, is really key to making the right choice between these two powerful balance tree structures. Definitely something to mull over for your own data management challenges.